Okay, so Moitreo, did you start the recording?
Yes, ma'am, I just started it.
Okay, great. So now I think we are live on YouTube. Let me share the link with everyone and yeah, the organizers, so that if you want to share it with others. Okay, so let me then start my video. Can we have the videos of the panelists? Oh, they're already there. Great. Very nice to see all of you. Urboshide?
Yes, Sritana, you can see me, right? Can you hear me?
Yes.
Yeah. Okay.
Yes. Can you all clearly hear me?
Yeah.
Great. So we'll sharply start at 6. Yeah.
Okay.
Just get.
Ma'am?
Yes.
And can you make Comrade as a co-host as he will be the
Oh, absolutely. Sure. Shobik, do you want to make him also?
Yes, ma'am.
Thank you. Okay. Yeah, I'll make Shomrat. Shomrat, I don't see. Oh, yeah. So did you all get the link, the YouTube link? So someone needs to watch that if there are questions on YouTube, if there are people watching it over YouTube, okay? Okay, so I guess first I will, so Shagnik, should I start? So you'd be hosting the set, you will be the, I have to.
Yes, ma'am.
You're going to start. Okay. So I'll just mute my micro.
So hello everyone. I am Shagnik Rai, a second-year student at Presidency Physics. So now we are going to have the panel discussion session of Precision. In this session, we will have several eminent physicists enlighten us about the future of physics. Some general instructions. Kindly keep your videos off and microphones muted. And if you have a question, please type it in the chat box. This session will be chaired by Dr. Sritana Chatterjee, who is also from Presidency Physics. So over to Dr. Chatterjee.
Okay, thank you very much, Shagnik. First of all, I want to thank our students who have been hosting Precision for the last 5 years. Since 2017, this is the 5th installment of Precision. And in the first year, we had the panel discussion. Of course, that was an offline conference. And then we didn't have it for the next 2 years. And then last year, we had a terrific panel discussion on physics during the pandemic. And we had Professor Shomak Rai Chaudhary, Professor Bindu Bamba, and Professor Gautam Menon as panelists. And so this is this year's panelists. We have a very, very, very distinguished panel. And I'm extremely thankful to all the panelists who actually agreed to spend their valuable time with us. And we are eager to hear from them. So let me introduce the panelists. So we have with us Professor Urboshi Sinha from Raman Research Institute. So Professor Sinha did her bachelor's from neighboring Jadavpur University. And then she went to Cambridge for her master's and PhD, and then was a postdoctoral fellow at the Institute of Quantum Computation, which is also affiliated to University of Waterloo in Canada. And then she joined RRI, I think, in 2012. Is that right, Professor Sinha? I think,
Yep.
2012. And has been now a full professor there. So Professor Sinha has had numerous fellowships and awards. She was the recipient of the prestigious Sharna Jayanti Fellowship, and she has been the Homi Bhabha Fellow from 2017 to 2019, and is now she is now the Simons Emin Weather Fellow at the Institute of sorry, in the Perimeter Institute. And Professor Sinha is known for her leading work in quantum optics. And a few years back, she was a colloquium speaker at Presidency. And if any of you were there as students, this was, I think, 3 or 4 years back. And there was a terrific talk that Professor Sinha gave us, and we get to hear about the beautiful quantum optics experiments. And we are sure that we're going to hear some exciting stuff from Professor Sinha today. Welcome, Professor Sinha.
So thanks, Sritana. Just a quick correction. I actually did not receive the Swarna Jayanti Fellowship.
Oh, sorry.
So just to,
sorry.
Put the math.
Oh, sorry.
Yeah.
I'm very sorry.
But
Very sorry.
Thanks
for
very
that.
much. Yeah.
Very sorry for the, well, you deserve more than Swarna Jayanti for what you have been doing for the last 5-6 years. It's fantastic work. And then we have with us Professor Tirthankar Roy-Choudhury from NCRA TIFR. And Professor Roy-Choudhury, Professor Roy-Choudhury did his bachelor's and master's from Vishwabharati University. And then he went to IUCAA for his PhD. And he worked with Professor Thanu Padmanabhan, whom we lost a few days back. And that was very tragic. So, and Professor Roy-Choudhury has worked on various aspects of structure formation. So after IUCAA, he was a postdoc at CISA in Trieste, and then he was a postdoctoral fellow at Cambridge. After that, in 2008, Professor Roy-Choudhury returned back to India and joined the Harishchandra Research Institute as a scientist. And then in 2012, again, Professor Roy-Choudhury moved to NCRA TIFR and has been there since 2012. He was also recipient. He was recipient. If Professor Roy-Choudhury, if this is correct, the Peria Foundation Prize for his contributions in theoretical astrophysics and many other accolades, and he has been leading tremendous efforts in the SK mission that India is part of, and doing a fantastic work on understanding cosmic reionization, and eventually, I hope, in 21st century cosmology. So we are very glad to have Professor Tirthankar Roy-Choudhury among with us today. I think you visited Presidency in 2017 for the SK conference.
That is correct, Sujata.
Yes.
Thanks a lot.
So welcome again. Although virtually. So welcome, Professor Sinha. Welcome, Professor Roy-Choudhury. Virtually. And then we have with us Professor Rajdeep Sen Sharma. So my association with Professor Rajdeep Sen Sharma goes long back, since 1998, when we were undergraduate students at the then erstwhile Presidency College. So Professor Sen Sharma did his BSc from Presidency College, and then he went to TIFR, where he finished his master's, and then moved to Ohio State University, from where he did his PhD. And after OSU, he was a postdoctoral fellow at Harvard University. And we have very cherished memories of those days. And then after Harvard, he went to University of Maryland and stayed there as a postdoc, and then came back to India to his alma mater, in some sense, TIFR, and joined the Theoretical Physics Division at TIFR, and has been a scientist there since then. So Professor Sen Sharma actually works on various aspects of condensed matter physics, and he has spoken, I think, 2-3 times in our colloquium and others. So if we have some students who happen to have attended Professor Sen Sharma's colloquium, would remember the remarkable discussions we had. And so I guess without further delay, so welcome, Rajdeep, to Alma Mater and to the session today. So I guess first, I would like to give just my impression of what I understand about the discussions that we hope to have today. Is I said, so there was some joke, I think one of the panelists shared this in one of their social media posts, that we are not going to be astrologers or I don't know, share market predictors or forgive me, COVID modelers today. So it's not really about oh my god, the future of physics. It should, I think, if my understanding is correct, then I would think that today our discussions will go in the direction of where the field of physics, both scientifically and in terms of professional standing, excuse me, will go in the next 20-25 years. So probably by the time our panelists, our honorable panelists, and maybe me, we end our career. So where do we want to see the field going? Where do we envision seeing this field going, and what kind of interesting problems we are going to solve in the next 20-25 years? And how do we expect our field to evolve? So that would be the core of the discussion today. If I think the panelists would probably agree with that. So I would now just ask, so we would start the discussion in this way, that now I would invite each of the panelists to sort of share their views on how they see the crux of the discussion today, and if in their mind it's really physics in the next 20-25 years, then what do they see as the most important and interesting problems that we hope to see solved, or at least partially solved in the next 2 decades of our lifetime. So I would first invite maybe go by, I don't know, seniority. So Professor Tirthankar Roy Choudhury, can you kindly tell us that what do you think our field is going, physics as an overall field, in the next 20-25 years?
Yeah, thank you, Sritana. So I should admit that when I received the invitation in this panel discussion and I saw the topic, I was like quite scared. I mean, future of physics is such a vast topic. I don't know how much justice I can do to it, but let's see how it goes. So, of course, I mean, if you talk about the future, the only person who can be sure and tell you what's going to be are the astrologers. And me is what the closest you are going to get to an astrologer. That's an astrophysicist. So what I will try to do is, I mean, I will try to stick to what I know. So I will try to talk about the future of rather the field I work on astrophysics. And let's see then, once we get input from all the other panelists, we will have some coherence as to where the full physics field is going. Now, to predict the future, what's going to happen 20 years down the line, at least in astrophysics, it's a very risky job. Think about what was the state 20 years back. If somebody had told us that we would have thousands of exoplanets, somebody told us we would have seen a direct evidence of a black hole, we would have detected black hole using gravitational waves, and I don't know, many other things. I mean, okay. I mean, I'm sure many people wouldn't like believe them. I mean, people know people bet with each other about the future, and I mean, many people lose and there are fights and so on. So yeah, I cannot tell you what exactly would be the problems which would be interesting in astrophysics. That would be a very risky thing to do. In fact, this question, if you ask to someone, it will really depend on the temperament of that person as to what they think are the most important like problems to work on. Again, if I take an example of the field I work on, let's say cosmology, if you ask someone, if you ask a person, they will say, oh, in cosmology, the unsolved problem is the nature of dark energy or dark matter. And then if you ask some other person, they will say, no, that's just too speculative. Actually, the problem is galaxy formation. And the first set will say, no, galaxy formation is too mundane. I mean, it's just too messy physics. So, I mean, that's not even important. So, yes, it's very difficult to answer this question very easily. But then, I mean, suppose you want to choose a problem, or when we choose a problem, do we just do a coin toss and choose? I mean, no, that's not also true. So the thing I would like to highlight here, the way the field is moving, the field of astrophysics, is actually driven by observations and instruments. So a lot will depend on the kind of instruments that are operating and will come up in the next decade, and the kind of science that will be done by them. Of course, in astrophysics, what happens is the moment you make a new instrument, it will do whatever you had expected it to do, and it will find out something completely unexpected, new discoveries. That's always happened in astrophysics. So the moment this new generation of telescopes come up, we really don't know what to expect. So if you think of a problem to work on, the only suggestion I can give is you try to work on a problem which is relevant for the observations and the instruments which are there, and the observations and instruments which are going to come up. If your problem can be linked to any of these, it will remain important. So it was important 20 years back, it is important now, it will remain important 20 years down the line. Of course, new things will get added, but as long as you can connect to the instruments, you are safe. You will do interesting stuff. And that is applicable to theoretical, observational data, whatever you are doing. And just to end my point, personally, I mean, if I stick to astrophysics, there are 3 questions which really I would like answers to in the near future if I can. One is, given so many exoplanets being observed, will we have some idea about life in a distant world? I'm not talking about really like direct signals from aliens, but maybe we will have some idea about some complex molecules at a distant galaxy. I mean, that's a lot of information. Second, we would like to really understand a lot of things about black holes now that they have been discovered, both in the center of our galaxy as well as all these black holes LIGO is observing. I mean, there's a lot of unanswered questions there, and I can elaborate later if we come to that. And the third is something which is close to my heart, which is the large-scale evolution of the universe. When the first stars form, how the galaxies evolve. Sritana will say the black holes in the center of the galaxy. I mean, how did they come about so early in the universe? So yeah, basically the large-scale evolution. So yes, so this is probably what I wanted to say in the beginning, and maybe I can come back again later. Thank you, Sritana.
Oh, thank you very much, Professor Raichaudhuri. So that was nice, and I'm sure we'll have more discussions. And as you say, that it really depends on whom you ask. What are the most important problems really depends a little bit on whom you talk to. So now I would invite Professor Urvashi Sinha to share her views on what she feels and thinks are the most exciting and important problem that as physicists and aspiring physics students should think of solving in the next 20-25 years.
Thank you, Sritana. Can you hear me well?
Yes.
So thanks a lot. And it's for a change, it's very nice to go second, because actually Professor Raichaudhuri set the stage really well by giving a very nice overview from the astrophysics perspective. So I actually wanted to make the last point myself regarding the exoplanets. So we have if we have a poll, then we are already 2, so indeed, so in the sense that currently we are in a situation that we really believe that we are not really doing a lot of good to our planet in many ways, right? So somewhere, there is this inspiration to figure out what is beyond. And so this particular research actually tends to that also. So this is more like a holistic thing. And in fact, although I don't work in it on this topic by any stretch of the imagination, I really believe this is something important for us to worry about and work on. So it is good that the question has changed from predicting the future to actually talking about what problems I would like, personally should be looked at in the next 20 years. So the prediction part worried me as well. So then, given that I'm an experimentalist, it's even more worrying. Because whenever we do experiments, they never really match with our expectations. So in some sense, prediction is something which is very difficult. So I want to give this answer in a kind of two parts. One would be, problems which I feel are of fundamental importance, which we have been looking at for the last couple of decades, if not more, and we should be looking at again in the next couple, because I do believe that we need to solve them, hopefully, and COVID permitting, in our lifetimes, right? So we really hope for a bright future where all of us actually meet again 20 years down the line and say, have we really solved these problems? That would be a nice panel discussion for Precision 2041. Yeah. So I would begin with, of course, the thing which is closest to my area, which is in quantum mechanics and quantum science and technologies and so on. It's also something which is very gaining a lot of importance currently. And so I see that it is something which would definitely be important for the next couple of decades, if not more. So here, while we are all excited about some of the applications that this field promises, my personal interest has always been in the foundations of the subject. So, fundamental aspects of quantum mechanics. There are many unsolved problems in the fundamental aspects of the subject. And in fact, if we don't solve them in the next foreseeable future, then the applications that are based on them also tend to get affected by that. So one of the things that I personally am very fond of is precision tests. So precision tests from experiment and theory of various principles, and of course the unsolved problems like the measurement problem. As we all know, the measurement problem is one of those unsolved problems in quantum mechanics and remains so. So I'm hoping that with all the efforts that are going on worldwide, we would have more convergence on this topic in the next decade or so. Then, of course, there is, whether quantum mechanics is the final theory. That is one of the, again, open questions, because there is a lot of research on modifications of the subject, and in fact, motivated by another, what I would say is the holy grail of theoretical physics, which is finding a theory of quantum gravity. Right. So this is something that has interested, I have family who is more interested in this problem in the sense that he is working on it. But then having said that, I cannot escape the interest in that myself. Right. So we don't yet know which is going to be this theory. There are lots of contenders, and, and they do like to talk to each other and, sort of claim supremacy, but we are not there yet. And so having said that, it is important because, of course, it has been in our perception as an important problem for several decades, and it still remains unsolved. So this is, in this order, foundations of quantum mechanics and quantum gravity kind of come together in some sense as important problems to look at. Then, of course, I would go to the application areas, which is quantum technologies, as we call them. And that has been, that has caught our attention for the last few years. In India, we've had too much attention on it, I believe. But then having said that, it deserves some of it. And so there are applications where, we are promising exceptional computing power, which is quantum computing. And it is actually going to be an understatement to say that there is a lot that needs to be done in that for this particular architecture or for this particular application to be actually relevant from a practical point of view. At the moment, we are sitting with these quantum computers with 50, 70, 80 qubits. And these are all proof of principle machines, which really are not showing that exponential advantage in the problems we want to solve. So if we want to solve a problem in drug design or healthcare, these are, coming up with new simulations, which will give us new materials. This is where we see the real advantage of such a machine. And that is, we are not there yet, for sure. And of course, when I started working in this field, people felt we will never be there, but that has changed dramatically. And so again, echoing Professor Roy Choudhury, that so much has changed in, for instance, astrophysics, similarly the same in quantum. So now we have physical machines, and we actually can say in the next decade, we will have these bigger ones, which will be practically useful, right? Similarly, we will have security, which is based on quantum technologies, which is quantum security, quantum key distribution. These are already very much being used, but then there are unsolved problems there. But this is a tricky one, Shuchetana, because we are talking about future of physics, but then when we talk about quantum science and technologies, we cannot just escape engineering. So there is going to be part physics, part engineering type, issues. So if we want to actually make our network completely secure, then one of the layers is the quantum, but there are other layers which need to also feed into that. And these are problems which have both physics and engineering aspects. And I'm hoping for this quantum internet in the next 10 years. So where the entire world is going to be connected through a quantum network of satellites and fiber and so on. So there's going to be challenges in physics, engineering, as well as mathematics, which we will be resolving in order to make this happen. So now I will shift a little bit from the quantum, because, it seems like Professor Roy Choudhury talks about astro, I talk about quantum, and Rajdeep will talk about condensed matter, then it's a little bit unfair. So I already started with the exoplanets. That was on my list, as the thing that I would really like to see happen. But then having said that, one thing we also should be working on much more than what we're doing now is alternative sources of energy. Because, all said and done, we are sitting here and, we are happy with the state of affairs currently. But then we do know that as human beings, we are not always being, what should I say, respectful of our resources on this planet. And so there are many things which we do, which perhaps are harmful to various things around us. And so sources of energy, if we come up with better alternative sources of energy, which actually can replace the ones we currently use, that is going to be a very important research area. And more so over the next couple of decades, where, we will be again competing with natural resources. And then if none of this works, then of course we will follow Professor Roy Choudhury to the other planet. And in fact, even if I don't want to hear from aliens, in fact, I actually do a little bit. I like Star Trek and so on. But then having said that, we really want to figure out in a scientific perspective, if there is life on other planets, then what is the kind of situation which is enabling it? And of course, not my area, but something I would really like to know. If it's only Earth which can support this, or are there other kinds of environments which is also supportive? Can we mimic that? I mean, lots to do in that domain. And in fact, in the proper science domain, not just the fiction. So I'll also stop for now, and of course, hope to contribute more as we go along.
Oh, thank you so much, Professor Sinha. That was very nice, wonderful. Me too want to hear the aliens a bit. I also like science fiction, have been liking for a long time. So now I would invite Professor Sen Sharma to give us his views about how he sees this issue and the progression of physics and the problems that we're going to solve in the next 20-25 years. Professor Sharma, please.
Thank you, Shuchetana. I hope you can hear me.
Yes.
I was the culprit who put that joke on the Facebook, I guess. So let me be clear to the people. But as I hope you have seen from what the previous panelists said, it was only half a joke. Predicting the future is really probably not giving concrete predictions is probably not a good thing to do either way. So what I would like to do is, traditionally when we learn or teach people physics, we take up areas of physics often in terms of energy scales involved, high energy physics, nuclear physics, gravity, etc. But for this discussion, I thought a slightly different classification might actually give us some idea of what can we say, and then maybe I'll say a few words about the part that I know more. There are, of course, areas in part of physics which are at least currently or in the foreseeable future without experiments or not being, but There people are trying to see consistency of various theories, what new kinds of theories are being possible, etc. Some of it, as people have said, you don't know that what is not possible today will not be possible in 20 years. I mean, 20 years is a very long time. But for now, and these areas, what happens is that they're flexible. Sometimes some of the questions keep changing. For example, in recent years, there's been a lot of influx from quantum information theory, partly as a result of huge sort of resources spent trying to build quantum computers. And I mean, that kind of thing has an overall effect on the physics community. So words like entanglement and so on, which were alien to, let's say, condensed matter physicists, or even, let's say, string theorists or quantum gravity people, and they have actually found very useful use of them. They're very interesting mathematical connections and so on. And so in these areas, again, it comes up because of some ideas come from various parts, and then you get a new whole set of physics questions that come out of that. So they're more flexible. The questions often keep changing. They become more and more interesting, and you get new surprises out of that. So that's one part of this. Most of the other parts of the physics are driven by experiments, although somehow in our country as a whole, maybe the overall, maybe the education system slightly biases people towards more theoretical research. We can come to that later. And in this case, you can talk about big experiments. Let's say you can talk about experiments which require more than 5 to 10 years to build. And in those cases, you have to plan. I mean, you cannot just say tomorrow, oh, let me have one telescope, and 3 months later, no, let us do another telescope. Or if you bring making colliders and so on. So in some ways, at least that is in there's a bunch of questions which are predictable. That does not mean the answers are predictable, and that does not mean, as Professor Raichaudhuri pointed out, that they don't throw up surprises, and then the whole field moves towards understanding these new surprises that nature has thrown up. So again, but at least often they have some sort of defined questions, because the machines are so big, so large to build, you cannot just build them and then destroy them and go on and do various things. So that's one set of things where things are more predictable. The next set of things, which is small or lab scale experiments, which are again much more flexible. And the questions, again, you will see that it's often driven by experiments, what experiments throw up to us, what challenges, and condensed matter falls in this part. So parts of maybe atomic molecular, optics, part of lasers, etc., throw up this kind of things. And in these cases, I mean, there is a very strong coupling between theory and experiments, often driven by experiments, but then there is a huge flurry of activity on the theoretical front, which informs further experiments, and then the whole field mushrooms. And just to give you one example, actually, I realized that, I started my research career in 2001, so it is actually 20 years. So let me give you what happened.
Congratulations, yeah.
There's just this 20 years. When I started doing my PhD, the biggest thing was, high temperature superconductors, understanding because they're very strongly correlated, very strongly interacting electrons, huge amount of interesting phenomenology, which kind of deviated from very well-known paradigms of how people had understood solid state for a while over some 30, 40 years. And that was the big thing. And that's, okay. As I was graduating, okay, so this was 2007, I'll tell you two things that came up. I think in 2004, people learned how to isolate a single sheet of carbon atom, which was called graphene, okay? And suddenly, people had to bring down things they had learned in high energy physics about Dirac equations and so on. And they went all in. There was a lot of technological aspects, but there was also a lot of understanding of what this new 2D Dirac material is going to do for you, okay? And realized that this whole interest came because you could isolate. I mean, people had talked about this. I mean, of course, people knew Dirac equations from way back, but this came because people could isolate, they could see, they could measure things that were there. And that got its own Nobel Prize, etc. And the other thing, gradually people realized is this is almost non-interacting physics. So when I was starting my PhD, there was this essentially almost various people saying that, you know, unless you are doing very strongly interacting electron physics, I mean, all of non-interacting physics is understood, essentially. And then you, okay, then this comes up. 2006, there was a theoretical prediction of topological insulators. Okay, what happened there is people said good old band theory, which we learn in maybe, you know, BSc solid state physics. Okay, you take that. There's more, and the basic ideas are still the same, but there's more hiding in those block wave functions that you learn about in your solid state course. And they have some topological properties. There are measurable things. You go to surfaces, there are states. And this came in 2005 in a set of papers. Actually, one of the persons who is less credited for this internationally is actually an Indian person called Rahul Rai, who wrote a fantastic set of papers, who was almost equally with Barnevik, Zhang, and other people who are doing this. But the reason it took off after those first three papers was that in 2017, there was an experiment which exactly saw what they predicted. Okay. And now if you talk to people in physics, topology has become the buzzword. I mean, sometimes overused, sometimes, but you know, that led to a wide range of things that happen from, you know, very mathematical things coming out from category theory, etc., to people really going on, can I make the surface better? Can I clean up the surface of a material to measure things? And this has changed even some paradigms of our thinking about many-body physics. Again, completely non-interacting systems driving, whereas when I started, people basically said all of this is understood. Okay. In 2018, so let me give you the last statement, which has come a full circle. People started taking two layers of graphene, which by now people thought, oh, we have got understood very well. And they just said, okay, let us twist them a little bit, their crystal axis. And they found something called twisted bilayer graphene. It was predicted in 2011 that they will have some sort of strong correlations. But in 2018, there was a series of papers which showed that this shows superconductivity, this show various things. And there's now a flurry of activity we still don't understand. Remember, we still have not understood high TC completely. So that old problem has not gone away. It's not like it's not worth solving it. Anyone who has worked in high TC will tell you that that's the problem, which is really, really worth solving. But all of this, and right now we don't understand how things are coming. So we went from highly correlated systems to non-interacting systems to twists on non-interacting systems, which are now back to highly correlated systems. So I hope what this tells you is that when I started in 2001, nobody will talk about topology, and there was a group which was talking in, you know, quantum Hall, etc., in strongly but no one was thinking of this kind of things. Someone graduating in 2010 would have no idea that people would be so interested in understanding this twisted bilayer graphene. So my point is that problems change. Nature throws up surprises. We react to that. That leads to often a larger class of understanding as happened from topological insulators and so on and so forth. And in condensed matter, this keeps happening every 5 years. Okay, so so if you ask me what I'll be working on 5 years later, I'll say whatever is, you know, has been thrown up. Okay, so that's the nature of things. That's the nature of how things evolve. And the last two things I wanted to touch upon a little bit was one is technological challenge, which Professor Sinha also touched upon. Quantum computing, quantum sensing. I guess Professor Sinha is actually doing a lot of interesting things there, part of it. Hydrogen storage problem related to climate change, other technologies to alleviate or slow down global warming, Can we have fusion reactors, and to what extent can we do this? The well-defined goals. There's a huge challenge in getting to them, and driven by technological innovations, more innovative experiments, and so on and so forth. And finally, there is the more broader expansion of physics ideas to biology, society, diseases. Again, very, very complex systems, and I don't think we have completely got the hang of even how to approach all of them. So in all these areas, you will basically see expansion, and you will see that physics will try to gradually ask and understand some of these problems. Coming back to the last part, where I'm supposed to talk about, what are the problems I think, which is of course now in my field, it will be in condensed matter. I guess one of the things, and again, as Professor Raichaudhuri said, this is very personal. You ask the next condensed matter physicist, you will get a different answer. And in condensed matter, because it's so broad, you will definitely get a different answer. You ask anybody else. So, but anyway, this is my take. One of the things that has happened over the years is this influx of ideas from quantum information, like entanglement and so on, into condensed matter physics. Now, that has helped us understand many things. Some people are trying to build new paradigms based on just entanglement and symmetry, or topology and symmetry and letter. What has not happened in this context, in many body contexts, this has happened when you are thinking of 2, 4, 5 qubits, and people know, people understand, people have measured actually. Again, an Indian person, Rajibul Islam, was very, very crucial in the first measurements of entanglement entropy. What is not clear, has not been clear, at least to me, is what all this means in terms of measurable things, not measurable in computers, that we can see in various cases. And can we make those connections much clearer, much cleaner? Can we measure entanglement, or in how big a system can we measure entanglement, and these ideas? That's one set of questions. It has both theoretical and experimental ramifications. What should we measure? And then can we go and measure any of this? The second I would say is non-equilibrium dynamics. In equilibrium statistical mechanics, there's a huge paradigm. You have, e to the power minus beta h, and then the question is, can you evaluate, and so on and so forth. But the paradigms are very well defined. I mean, we teach them in undergraduate courses. Non-equilibrium physics, this kind of paradigms are not, it's not even clear that you can get for every situation, but some more classification and understanding of this kind of, these are the big theoretical things that I think are happening. And going back to standard condensed matter, okay, I can say in one word that, can you understand how very strongly interacting electrons behave? But that probably encompasses a large class of condensed matter, both theory and experiment. Okay, so I'll stop here, and then we can come back.
Okay, thank you very much, Rajdeep, for sharing your views on the issue that we're discussing. Now, I just want to mention two things. So we had one of our panelists as Professor Amitava Raichaudhuri, who is a very respected, very senior particle physicist, and we all know. But Professor Raichaudhuri actually he had a medical appointment, so he really asked me that he wants to apologize. He just wanted me to tell you that he could not attend today, because we do have missing representation from particle physics in this panel. But I guess we might also discuss some of the interesting, because the next topic that I'm going to come already, which has been outlined by Professor Sinha and Professor Shen Sharma, is that, and we have many questions, very interesting questions coming. So one thing we can do is just discuss these two topics also in the light of the questions that the audience have put out there. So we spoke, I think you have mentioned machine learning some aspects. And so artificial intelligence, its role in solving all of these problems that many of you and all of you actually put through. So the role of machine learning, we know, I mean, I have students who are doing quasar classification to students who are studying quantum chaos. All of them are using machine learning algorithms to solve this problem. So it is my understanding, and I'm sure you will also share, that this has become really very important in physics, and we have some very interesting questions regarding that. The other is interdisciplinarity, and I think the panelists, as they said, that and Rajdeep also gave some distinct example that how these sub classifications and all things, I mean even just outside of physics and biology, they merge, and we have interesting problems. For example, the planet of the exoplanetary science, we know that we have exobiology. So that's something that's very interdisciplinary, combining biology and astrophysics maybe. And there are many things, many such problems. So if we want to solve these important and interesting problems, I think we have the role of machine learning, usage of artificial intelligence, and also this crosstalk between disciplines. So I would actually take some of the questions that are related to that. I see a lot of questions coming. So one is from our colleague, Sritana Chatterjee, who was actually the moderator for the panel discussion last year. So Sritana has a fantastic question. Earlier this year, MIT physicist Max Tegberg used a machine learning algorithm for auto-discovering conserved quantities using trajectory data from unknown dynamical systems. Is it possible that such kind of brute force search for desired analytical results will replace a large fraction of traditional theoretical physics research? So do you think any one of you would like to take that question and expand a discussion on machine learning and what role can it play in solving some of the problems that we discussed today? Urvashidi, do you want to go?
Yeah, I can go first, but then so regarding Ritoban's question, I am of course not familiar with the work that he's referring to, but having said that, what I find, I mean, machine learning is an algorithmic tool, right? Yes. So essentially, if we are talking about what problems would be interesting in physics in the next 10 to 20 years, I'm a little, confused as to how we can treat machine learning as something other than a tool to solve those problems, right? So machine learning is not a physics discipline.
No.
Yeah. So then in some sense, we can use such learning-based algorithms to reach faster convergence for some of the problems that we kind of highlighted, right? So for instance, in my own domain of quantum science and technology, we are actually using machine learning algorithms to actually, for instance, in quantum optics experiments, they are being used to come up with, faster convergence for various sorts of analysis. One example is estimation of the quantum state. So you know that you can't just estimate the quantum state by one measurement because you destroy it. So you have to come up with some techniques by which you can reconstruct it. And so in this reconstruction, there are very interesting results where they have used ML-based algorithms to kind of reach this reconstruction result faster than the traditional quantum state tomography approach. So this is a very, this is an example that is of interest, I mean, for an experiment, for instance, which we are working on. So it goes down to using such learning. I mean, machine learning, I'm not a, computer science, traditional computer science person. I mean, I work on in the quantum domain. But having said that, what I find is that, this is a very handy tool to kind of speeden up certain things and also to make certain things possible, which otherwise perhaps would take much longer in the optimization. It's an optimization problem, right? So essentially, we had these traditional optimization techniques, which we were using for various data, analysis and experiments. But now with the learning thrown in, we are reaching convergence faster. So in fact, there is this field which is AI-inspired quantum computing as well. So essentially using artificial intelligence to augment quantum computing research. And so on and so forth. So this is, so if you ask me, I would say that instead of, I mean, we shouldn't get, we should realize that machine learning is a tool to enable some of these physics problems that we have been outlining and more, but not necessarily a physics problem by itself. Yeah.
No, I don't think that this is a, so I didn't mean
it's
that.
A tool, right? Yeah.
It's a physics, but I think maybe the question should be put in this way, that should we be then doing a lot of crosstalks with computer scientists, or, I don't know, computer scientists, mathematicians,
sure.
to sort of solve the important problems that we think we want to solve, and, use AI there. So I think I just asked for your take on that aspect.
Right. So, I mean, for instance, so this is more hinging towards your other point, which is interdisciplinarity, right?
Yes.
So then in some sense, of course, that is, if we, for instance, people like us, we are traditional experimentalists. So we are working with the experimental architecture, we're building experiments. But then talking to people who are from the core quantum, from the core computer science background, we actually learn a lot about how to use those techniques towards our experimental analysis, and also setting up more next versions of the experiment itself. So there is a lot of feedback there. So for instance, just to give you an example, a problem that we are currently working on is called satellite-based quantum communication. Okay, and so it's of course a problem which is much larger in scope than an experiment. One experiment that I may be working on, in the lab. So this involves actually connecting different parts of the earth using a satellite as a trusted node and having secure communication between these different countries, and in our case also within the country. So you can imagine that we actually need to have our team actually consists of course physicists, but then we have people who are coming in from a computer science background. We have people who are coming in from the satellite communication background, yes, which is very different from our core area. Then we have engineers, we have people who are doing FPGA. So indeed, this is an example of a project which involves quantum physics, but then it also involves algorithms. It involves some, we are actually trying to come up with ways in which we can use, some adaptive optics tools to make this better. And that is where a learning-based approach is coming in. So indeed, that is, something which is becoming the flavor of many problems we are attacking, as a physics community, where we cannot just remain, in a shell, just thinking about that, but we have to talk to other experts who will bring in more richness to the problem. And as an example, I just gave something that I'm personally, of course, working on. But regarding the interdisciplinarity, whenever any point of view I have, it always comes with the other side also a little bit. So one should, of course, realize that not every problem needs to be interdisciplinary. So, there is this new thing, that if it is interdisciplinary, that is the thing that gets funding in our country for research. And so that is something which may not always be true. There are problems which actually are very important from the particular perspective without being interdisciplinary. And so there are different classes of problems. And so the role is, of course, very problem dependent. So I gave an example where it plays a very significant role, but there are other examples where it need not be necessary. So, yeah.
Yeah, so I guess, so the take is that we solve the interesting problem that we think is interesting. And for that, if we need to do crosstalks among discipline, we go and do that. For that, if we need to learn AI algorithms, we do that. But I guess our focus is that we want to solve the interesting problem that we are solving. So, Professor Raichaudhuri.
I wanted to take up Ritoban's question because, probably because Stegmark is someone who works in our field, we all noticed the paper and I found it really interesting. Of course, I'm not an expert to tell how this field will evolve, but I think one of the points, I saw Ritoban's message. Ritoban is asking that whether the way we do theoretical physics will change, because there is some machine learning which it seems it can find out conserved quantities on its own without knowing anything about the physical system.
Yes, yes.
Now, again, I mean, I personally am quite excited about such things, but think about how theoretical physics itself has changed in the last 20 years. So this is something I will do every time you ask me a question. When we were like doing our BSc, MSc, we thought that integrations, differentiations have to be done in pen and paper, and there are some aspects where you go to the computer and do it numerically. And then theoretical physicists will actually work formulae, I mean, pages and pages of calculations will go. And then something called Mathematica came and immediately changed the nature of theoretical physics to a large extent. But it does not diminish the role of the physicist. The problems have to be still devised by the physicist, and there I completely agree with Urvashi. By the way, I am addressing my fellow panelists as Urvashi and Rajdeep, and I'll be happy if they call me Tirthankar, because Professor Rai Chaudhary, it seems like we are talking about Amitabh Da, Sriruddha, Pramod or someone. So let's not make it too formal. Okay. So yeah, I mean, if it's okay by you. So I completely agree with what Urvashi is saying. So it's a tool. It's going to remain a tool. It's going to give us a lot of leverage. I mean, of course, it's already giving a lot of leverage in numerical algorithms, numerical problems. It may change the nature of theoretical physics quite a lot, like analytical, theoretical physics, the way we saw Mathematica doing it and similar algorithms. But yes, I mean, finally the brain has to be supreme, and that will still remain. So this is just a pointed answer to Ritoban's question without going into anything else.
Thank you very much, Tit. So as we all call you, so yes. Since you insisted, although I call you Tirthankar Da, but it's okay. So I guess we are getting all these very interesting questions from the students and the audience. So should we go to the question session, or because they are very interesting and a lot of it are coming. So I would leave the panelists to decide that what do you wish to do now. What do you think? Because already I can see 10-12 questions already.
It's your call, I guess. I mean, we are fine by whatever. I'm fine by whatever you decide.
Absolutely, yeah. I second that.
Okay. So I think there are a couple of questions about the energy resources that Urvashi spoke about. So I think there's one question by Obhinandita Sinha, who says that energy resources are in danger of scarcity and shortage in the future. Can we come up with alternatives which get regenerated or replenished of their own, like a type of reuse and recycling? So I think the question is that it's automatically, so you make materials which you can use for reuse and recycling. Is that the question? On their own, okay. So replenished and regenerated on their own.
Well, we already have one such, right, Shuchitana, the solar energy.
Yes.
I mean, sitting in India, that is something we have a lot of. We have a lot of sunlight, and so then, I mean, of course, that is a very important area of research, and it is, something. It's not new. But having said that, from what I understand, and of course, I'm not directly from the field, but from what I understand, the the efficiency of this, the solar energy sources still needs to go up. And so then people are trying to come up with better, means of actually being able to capture this and preserve this and then use it later, which of course is something that is ongoing, and I'm sure it is going to become more and more efficient. But having said that, there are now apartment complexes where, we have this solar energy being used for, hot water, for instance. So, the heaters and so on,
so definitely we have an alternative source, which is the solar
energy.
Have. So we have the wind energy.
Wind energy as well. Yeah. But then I think the thing that we need to also think about is that these are the things which are already there and they need to become better. But then having said that, their usage should not be for what I just said. I mean, in fact, the one usage we should be looking at would be to have, vehicles which are running on such energy sources, because then we would be actually helping the planet. I mean, the whole idea is to reduce the emissions from various, conservative sources of energy and replace them by things which do not add to the pollution. And so the usages also need to be a little more, I would say, more thought needs to go into that. But then, yeah, so there are already examples, and I'm sure hydrogen would be another one, right? So there would be different examples, and I'm sure more will come up in future. But having said that, yeah, the answer to the question is yes, that is what we need to do. The question is whether we should be, investing in that, and clearly we should be, given where we are.
Okay, I see Shuratna, she has raised her hand. So Shuratna,
So, Sritana, maybe just one more comment I can make on
Sure.
this a little bit, which I think she tried to touch on towards the end, is that, these regenerative things which are there, nature has given us, are also fickle. The wind
Yes.
can stop, the solar, you can get a cloud, and so on. So if you are going to be using them, the biggest challenge there is to, when they are there, create and store these things in a way which is not creating more emissions and so on, and then use them, because otherwise these will always have this issue. There was this issue recently in Netherlands, I believe, where they went onto a huge power cut because part of this kind of an issue. So that's where hydrogen, I mean, how much energy density you can store in a material which can again be extracted is the question that comes up when you try to use this as from a more material science, or from a more, if you wish, physics / chemistry. It's actually more chemistry perspective and so on. So that's where a lot of research, I think, is happening in that part.
Okay, thank you so much, Rajdeep. That's very useful. So we have a couple more questions on these energy resources, but then I do see Shuratna
so I was just typing my answer. So it was in reply to what Ritovanda has asked. So this is like whether artificial intelligence can actually overtake the theoretical approach, the traditional theoretical approach that we have in our physics for such a long time. I don't think that can ever be possible, as because there's no representative from high energy physics sector today. Professor Chaudhary is not there. He could have said very easily how we came up with this standard model, this SU3 cross SU2 cross U1. That's a phenomenological model, right? So we looked at the experiments, and we tried to build up the model. And this is not something which came up from underlying symmetry of the nature. We came up with this theory phenomenologically. So that kind of thing cannot be replaced by a machine. So we have to look at experiments. We have to come up with theories. We have to, again, check the theories with the experiments, and sort of like that it goes on. And I don't think a machine can ever overtake and do that thing. It can definitely, if you give a theory, it can find a symmetry, but that symmetry may not be the symmetry of the nature. So we have to find out by ourselves. So that's what I wanted to say.
Yeah. So I
Maybe
guess as all the thank you so much, Shuratna. So I guess as the
No, Rajdeep probably has something to add.
I was trying to say that when Max Tegart was doing his things, he was actually feeding data, which he got from some simulations, but it could have been obtained from experiment as well. So of course, he knew what he was looking for, conservation laws, symmetries. These kind of principles had to be provided. But the machine learning was actually looking at the data. That data could have come from even other things. So, however, so that's one thing one should keep in mind, that actually machine learning is more used to getting data as input and then coming up with whatever
ideas. Yeah. So I guess as all the panelists also told it very strongly, that field is physics is an experimental subject, and as Shuratna pointed out, that standard model came based on our knowledge, our phenomenological knowledge, and that's not something that we expect our machines to solve, definitely not solve in the next 20-25 years. So I think there is regarding this, there's an interesting question from Aritra Kundu. So who is just a MSc student, just got his MSc degree. So my question is sort of based on what Professor Sinha said about alternative energy resources. As Professor Raichaudhuri said, that we have come a long way in the past decade or so in detecting phenomena which we could not have possibly imagined. And that was also said by, that was also pointed out by Professor Shen Sharma, by Rajdeep. And the key role behind this is our technological advancement. So my question is that in the next 20-25 years, what are the steps physicists should take in reducing the carbon footprint due to our technological advancement, of course, other than going to another planet? So the question is that we have all these technological marvels coming, and we are using them to solve all our problem, quantum internet or whatever. Now, question is that the side effect of all those, how do we have a sense of how they are going to affect us, affect the planet, and what is that we should think about it? So anybody wants to take it? Because we actually had a talk by one of our students, I think it was along this line, that they were trying. So I guess one of the issues, of course, is that we have to make these materials which are efficient. Am I audible to the audience?
Yeah, Sritana, you are audible. Yeah.
So I guess the question is that if there is something that we can do to sort of counter this carbon footprint that we might be generating because of extreme
maybe I can say a couple of things about that.
Or
so maybe I can say a couple of things about that. One is that, of course, there is a part of carbon footprint which we as human beings are doing. There's nothing special about scientists. I mean, we travel, everybody travels, you put in a car, all sorts of such things are happening, and that whatever we need to do is nothing specific to scientists, I guess. Then the only question is, for example, you are running huge amount of computers and they are generating emissions, and
I think Rajdeep, I cannot. Sorry, Rajdeep, I could not hear you for a few seconds. I don't know about others.
No, yeah, you got frozen a little bit.
Okay, is it clear now?
Now we hear you.
Yeah.
So I was saying that
yes,
but if you stop the computations, you are also probably not going to solve the problem. So probably want to focus more on finding more efficient ways of running this. There's lots of research which goes on into finding energy efficient microchips and stuff like that. So if you are, depends on, if you think that that is the problem and so on, then that's an area where people can contribute. I would like to point out one thing much of these problems, when you get to the heart of it, are not just about solving some elegant solutions or things like that. Most of those things, the basics of chemistry, basics of things are known. It's a lot of search and figuring out which part of it from experiment, part of it from simulations, AI can play a role, and so on. But that's the kind of research then one should try to do, and so on. That's one thing where you can probably, specifically as a scientist or a physicist, footprint you can try to reduce.
Okay, thank you very much, Rajdeep.
So
we have a couple of...
Sritana, if I can just add, I think there is a lot of awareness also we should appreciate within the scientific community in trying to reduce carbon footprints because of their technologies which are being developed. For example, all the future telescopes which are coming up, they are very concerned about these things, and many of the power will be solar based. Again, I know about the SK very well, but that same thing is happening in many other instruments. So that's something to keep in mind. So I think there is awareness. It's not an easy problem to solve, but yes, I think we will get there. We will find solutions as we go along.
So there was a question long back by Abhinav Singh, who says that, I think this is for Tirthankar, that you have told that it is risky to choose astrophysics for next 10-15 years. I don't recall you actually saying that.
No, so maybe I can clarify. Thanks you asked this question. So no, what I meant to say was that it's very risky to predict what is going to be the most important problems in astrophysics in the next decade or so, because the situations change so quickly. And I'm glad that Urvashi and Rajdeep to a lot extent agree with that. So yes, so there is no risk in choosing astrophysics. There is no risk in choosing any branch of physics. You should do whatever you enjoy. So there's no, I mean, there should not be any confusion in that. And what problems will become important, you have to be just aware of the field. Yeah.
And then there is an interesting question from Aparajita Bhattacharya for Tirthankar, that what do you expect to see in the upcoming decadal survey? How much of an effect would you say it will have on the future landscape of astrophysics, especially in your subfield of interest?
Thanks. So yes, so I guess they meant the US decadal survey. So of course, I mean, those are very important, and since US often turns out to be the global leader in many branches of science, they affect us in various ways. Unfortunately, I am not a great follower of what goes on in the decadal survey and what's going to come up and so on. So rather what I want to give you is where the Indian science, how the next decade or so is looking at. So again, I mean, if you think about funding and projects that are coming up, there is a lot of stress I see. Whether it's good or bad is not for me to comment on. There's a lot of stress on things which are big, the mega projects and like big things which are coming up. And then again, this is both in at least high energy physics and astrophysics. Again, the two fields I have kind of closely seen. There's a lot of stress in building instruments, and that's not bad, because that's going to give us access to like very high quality data and experiments. So it will at one level, it will help us building technology within the country, because we'll be building things for these instruments. Second, we will have direct access to the data, so we will actually be doing cutting edge science. We don't have to wait for somebody else's data which is given to us after taking out all the juice. No, I mean, we will have direct access to really high quality data. So that opens a path for both experimentalists as well as theorists, because theorists can start on working before anybody else. And I can see, in this sense, I'm quite optimistic for the next. I mean, I'm actually envious of the current students in some sense. I mean, they will have access to so many fantastic facilities which we didn't have, at least when we were doing PhD. We were, yeah. So in that sense, yes. I mean, next 10 years, we will have many facilities which are going to come up. I'm not talking only about astrophysics. It's a wide branch of physics. This is going to happen. And yeah, students should only stay tuned.
So yeah, I guess, so Debanit's question and Ognibho's question, Debanit's was relating like what are the prospects. I think that has been answered, that students should be working in problems they're interested, and there is no risky problem. You should be willing to take the risk because we don't know what. And then we have, so Ognibho was talking about the role of machine learning. I think we have a discussion about that already. Now there's one question from Shubhadeep Bhattacharya. So as Tirthankar said about the future of astrophysics, so I think the question here is related to what is the future of quantum computing in India? So maybe
I could take that question.
Yeah, sure. Yeah.
So what is the future of quantum computing in India? So I, for instance, see a very bright future for this field, given that, you know, in order to, I mean, I kind of would echo what Tirthankar said, that, you know, there is a lot of thrust on large projects, on lots of, you know, building of large experiments. And so quantum science and technology is also in that domain. And so there is a lot of thrust from users as well as agencies to actually fund such research, without which, of course, there won't be a bright future for a field like this, because it does require investment, quantum computing. So quantum computing and, of course, quantum sensing, quantum communication, or I'm going to include all of them in the umbrella. So if I were to make a 10-year prediction, and again, not from the astrology perspective, but simply because I'm aware of what would be the next steps perhaps that we would be doing, I would say in 10 years we would have our own large number of qubit quantum computers from different architectures. So solid state, photonic, and hybrid, and so on. So it's not just going to be a superconducting processor, but we will have semiconductors, we will have photonics. So there is a lot of thrust in, and there are upcoming labs which are working in these different diverse domains. So we should have quantum registers. So I don't like the use of the word quantum computer, because it's very difficult to define what is a quantum computer. So because these machines are actually tailor-made to solve certain classes of problems. So then these are quantum registers consisting of a certain number of units of whatever it is, right? So we are used to qubits, but then another thing, and this is something I always say whenever I'm asked a question of this kind, which is quite often, that there are other countries who actually have been working in this domain for much longer than India. If our lab is the first one in photonic quantum science and technology, then you can imagine that it's not a very old field in our country. There are other labs which are, other than NMR-based QIP, which Professor Anil Kumar started at IISc. Other than that, most of the labs are in the, within the last, decade, right? So then naturally, it's a young field. And so we have other countries where there have been developments which have preceded the ones which we are going to do. So it is very important that we realize that if we have to play a leading role in this domain, then not only do we have to work on some of these standard problems, which is about making a quantum register with a certain number of qubits, we also have to come up with unconventional problems which others have not yet thought about. So again, Tithomko said that the brain is something which is going to still remain quite supreme. So we need to use that to the best of our, because we have the scope now. So for instance, we are working on something called higher dimensional quantum information and quantum computing. So instead of qubits, using more than 2 degrees of freedom. So that actually is a much more open area, and there is a lot of interest globally, but then there is a lot one can do where we can make novel contributions. So if I come to quantum communication, the same thing. While we are all interested in there is a little bit of capacity building that is happening in this field across various labs, but we also need to come up with new protocols. So higher security, higher key rate, lower error, so new protocols which may not be already existing. So not everybody has to do the BB84, which is the first QKD protocol. So similarly, we need to come up with ideas in quantum sensing, and because that is another area which has a lot of application, that we can work on. So in the next 10 years, it is going to be even more important a field than what it currently is, because the people who are now starting to work on things would have already established a lot of success in the next 10 years. So one thing that the students need to do, and this is something, again, if people have heard me in any other forum, they will know I'm going to repeat myself. And that is this, that they cannot undermine the importance of experimental science. I mean, while we seem to have a bit of a Bengali bias in our panel today, but having said that, and again, I'm going to anger half the panel here by saying that Bengali males have a predisposition for theory. Okay, and so then, having said that, I'm sure the panelists are all very broad and so on and so forth. But then this is just an example. I'm talking at Presidency University Forum, so I'm sure there are lots of Bengalis in this discussion. Theory is great, but then in a field like quantum science and technology, theory plays a very important role to enable the experiments. So, I mean, experiment is not just about, tools and, twiddling some parameter or something. This is a very bad, very wrong mindset. So if we have to play an important role in the next 10 years, we have to be passionate about the experiment and theory combination, and especially in the field that I represent. Otherwise, of course, we really don't see ourselves doing anything revolutionary. in the next decade. And so this is where, we need to ensure that we enable the labs which are coming up, which are already there, and contribute to the efforts within the country. And that is something very important, that we now have a lot of good facilities within the country, and the students need to, develop a bit of nationalistic fervor and contribute to the efforts there, so that, we actually, this will help us in actually reaching that higher level, right? And so this is something that I definitely would add as being, our future will be bright if all these things actually also come in. Yeah. So
Okay.
I'll stop there.
So yeah, thank you very, yes.
Maybe I want to
Rajdeep.
add one point, actually,
Not on the Bengali mail one, huh?
No,
Okay.
that's fine. I mean, that's not about the Bengali mail one. In fact, I'm basically trying to say the same thing as you. What we see when we get students a lot, even when we are teaching, is that you pose the same problem in a mathematical way. Say a perturbation theory, you give them H0, H1, we have very well-trained students who can do that. But the moment you ask it in a language which is a physics, like give a physics problem, tell a story, and then ask what is the answer to this question, I think somehow, at least, and we do get a lot of students from Bengal and so on, we find that, there's a distinct lack of appreciation that, that math is going to be used to actually answer real life questions. And this probably goes back to the question of, even if you're doing theory, you need to have sense of what the experiment, otherwise you can't even help the experiments, you can't look at the nature. And somewhere changing this, our education system is very biased towards a very mathematical sort of education for physics, and somewhere changing that, I think, is going to be crucial for many of these advances to take place.
Yeah, so I think,
again,
yeah, so I think both Urvashi and Rajdeep, they have put out some very important problems that we really like to discuss in this forum. And I think, but then there are two questions, and one of the questions is kind of related to that, because it's absolutely true. I mean, when I was an undergraduate or master's student, I mean, it was like very much textbook based. And what Rajdeep said is, we really were, we were not really trained to appreciate that, oh, you have you just perturb your Hamiltonian and do the calculation, but when there is a really real problem, you can't connect it. So it's very much biased toward how we teach physics, and maybe we can have some discussions, if time permits, on how that can be addressed in the future. But before that, there's a question from one of our students, Shaumadip Kundu, who says that we can see some fields like astrobiology, sociophysics, and econophysics. What are the future of these interdisciplinary fields? So, Rajdeep, do you want to have a take on it?
Yeah, I think a lot of research in interdisciplinary fields, in fact, I mean, we don't understand them. I mean, not even as close to as, we don't understand many physical systems, like, inanimate systems. We definitely do not understand many of these systems, even close to what we understand other physical systems. So there's a very bright future. And just about a question about risk, I would like to point out one thing. When people are saying it's risky, things change, you should be happy with that. You are not starved for problems in your 30 years of career. Things change, you move, there are new problems, interesting questions. You are never really starved for interesting things to take on a whole career of 40 years. But anyway, coming back to this question, I guess they have very, a lot of things need to be done and would be done. I would just point out one thing, which is that interdisciplinary research is very, very good and very helpful. I am not quite in favor of interdisciplinary education or training, which there is a lot of noise, at least in the Indian community, towards making that happen. I feel that people who are well trained in one discipline, when they actually go and then talk to people who are well trained in another discipline, that's when fruitful interdisciplinary research happens. Because of constraints of time and so on, it's very hard to teach people one discipline well. So, when you try to teach too many things, you basically teach a set of problems. And that creates its whole lot of its own issues. So I would basically say, get well trained in one traditional discipline, and then go and talk to people who are relevant and try to solve this problem would be the way to go.
Okay. Thank you so much, Rajdeep. So we have a couple of questions on, I think, two broad themes. One is actually, I mean, a lot of students are asking that, we use a lot of computation in solving research problems. What if programming is not taught properly? There was one question about that we have some fields of research where the pen and paper kind of calculation still exists. So it's about taking the computer and pen and paper. I think these are all related to the educational aspects of physics, that how we actually teach physics to our students. I think if we have some discussion on that aspect, we can address some of these questions. And then there was another question about representation. So I see that do you think that communities were underrepresented in Indian physics 20 years ago are represented more now? I don't know if we'll have time to talk about representation, but that's a very, very important thing in the sociology, not only of physics, but sociology of all disciplines, that how do we make it more equitable? How do we make it, we give opportunities, and we just hunt talent all through it. So we'll see if we can discuss that. But I would ask the organizers, they said that it ends at 7:30. So can we, if the panelists are available, maybe can we take 10 more minutes? Is that possible? Because if we start discussing about physics education, I don't think in 7-8 minutes we would be doing justice to that how should we rethink or try to address that how we teach physics to our future students. So
yeah, 10 minutes is fine for
fine with me. Yeah.
So maybe I think this is a very important topic, and since we have a lot of undergraduate and master students in the audience, I think probably first ask Rajdeep, who actually brought this point of how biased our education system is toward training people in certain kind of skills and not training people in certain other kinds of fields, where all of those are needed to solve the interesting problems that we discussed today. So Rajdeep, do you want to share your views on that? What should we really think in terms of classroom teaching, maybe in the next 20-25 years? How should we evolve as teachers and also as students, probably?
Yeah, I mean, I have given some thought to it, mostly as I started teaching here students. So, I mean, we can talk in more generalities, of course, but I can tell maybe a few concrete things that we can do. How easy or how hard, I don't know. One of the things that happens when we teach is theory and experiment is often treated as binaries. Okay, we have, of course, that's partly logistical. We have labs and then we have classrooms and so on. I think what we need to do is we need to integrate more, like, things that you are learning in lab are really taking up in a lab should be represented in classrooms much more, and details, etc. Second, we have a way of thinking where most questions that we ask students to solve, they get basically marks for essentially giving one and only one answer. Okay, so this gives people that we also tend to give them problems which are exactly solvable, partly because they're easy to do. So a lot of physics actually involves being able to make good approximations, even as a theorist. And for that, you need to know what you are talking about. You need to be able to see the experimental data. Okay, I can do this here, not do that here. And this whole thing kind of goes missing. So give a few open-ended problems which are not exactly solvable, which they will not have answers to, and try to see how people progress. I try to do this, not very easy to do this, at least in the beginning of my courses. For example, this time I sent them a video of a top, which I took. I had a top toy, and I said that, okay, you have learned all the equations of tops in your classical mechanics. Now just analyze the video. And then there were a bunch of particular questions. Can you find the mass of these? Can you find this? Ask questions that you would actually like and would make connections to, and not just, can you write this Lagrangian, and can you write this equation of motions, and that sort of thing. So approximate things. Third, when we are teaching this kind of methods, let's say perturbation or whatever, try to give problems where, it's like, I know if I give the people a problem where I say lambda, they will do a perturbation theory. And I have had this experience where, I give the same problem. I say, this is, 10 to the power minus 6 or minus 3. And the people are still, you didn't tell us to do perturbation theory. So there's this idea that, you have to tell students exactly what to do. And I think that needs to change, at least within the classroom environment. And one concrete thing maybe we can do, and this is one concrete proposal, is to come up with a more repository of problems, and with a bigger collaboration of people at the level of undergraduate. This, by the way, happens at the plus 12 level. Okay, at least, there were all these problems, weird problems in Nirodov, where an ant was moving on a spinning wheel or something. But the thing that you have to take out of it is convert it into a solvable problem, and then nobody gave you the Hamiltonian, Lagrangian, etc. So maybe one concrete proposal would be to have a group of people sit down and start thinking carefully about it, and make a repository of problems which ties up, and then it ties up with more interesting things which are at the forefront of physics. Another example, when you have a string, okay, this we all do in continuum mechanics at some level, okay, then you put a weight on the string and so on. Now this is a very toy model, but this is actually a toy model of how LIGO does vibration isolation. Part of LIGO. So I think that aspect, and it's hard to find, and I'm giving you 2 or 3 examples which I have figured out, but it's probably a good idea for people to sit down and start with these examples and create a repository from which people can then make this kind of, that would be one concrete suggestion I would say. Approximations, don't go for solvable problems, make connections, and even if you have a solvable problem, there should be a next question which makes it more realistic and makes it unsolvable, and then people get a sense of what it looks like. This would be particular concrete suggestions rather than
okay. Thank you very much, Rajdeep. We have been all doing experiments in class on how to make physics teaching really more close to reality, because I think all of the panelists told multiple times, and I really like this quote that I say to the students, is that physics is a dialogue with nature, not a monologue. So since you are talking about the experimental aspects, because physics is actually an experimental science. So yeah, about physics. Yes.
So I mean, if I can just add on what Rajdeep said, and probably also it was there in the question. I mean, in addition to problem solving, we have to now think of numerical analysis.
Yes,
just like we do mathematics, like differentiation, integration, we have a mathematical physics course. We have to integrate numerical analysis into our curriculum. So like in classical mechanics course, you will give problems which can be solved analytically, but there should be a few problems which have to be solved numerically. They have to write codes. And believe me, there is no other option if you want to do like research in physics. Numerical programming is a must, in addition to theory, experiment, open-ended problems. I mean, even in numerical problems, you give open-ended problems and you innovate, and you teach a numerical analysis course, just like you teach a mathematical methods course. So yes, that has to be integrated in the curriculum. I'm sure it will happen in due course, but I think it's very important.
Yeah, so I guess if I should add that, then if you see the new UGC curriculum that I think all universities in India have been following for the last 3-4 years, now they actually have a mathematical physics course and the lab. So every theory course is accompanied by lab. And I guess for the mathematical physics course, they actually have the mathematical physics lab where they actually teach Python to the students. So we have been doing that quite successfully. And this is something that we definitely tell the students that, yeah, I mean, don't see numerical problems differently, like you don't see experiments differently. Experiment is part of what you're learning. It's not disjoint, not binary. Same for numerical analysis and doing pen and paper calculations. They are not binary.
Shuchetana, regarding experiments, I just wanted to add that maybe we should have better experiments, because we seem to have the same sort of experiments, pendulum,
absolutely,
Newton's ring, and actually, finding the value of small g. So I know of an incident in Calcutta, and I won't take the name of the university and so on, because that's a bit, but then having said that, somebody found a value 9.78 plus minus point something meters per second square. And he was asked, what, 9.8 Pelina? How come you actually ended up? So, I mean, so this is an example of what shouldn't happen, right?
Yeah.
I mean, somebody goes and does an error analysis and comes up with a range of values for this quantity. And he's asked, why not 9.8? Everybody's been getting 9.8 for the last few decades. So this needs to change. Yes. And depending on where your center is, some values change, presidency, this is the value. If you go to Ashutosh College, this is the value. So this also is known sometimes to students. So, this is not actual how experiment should work, right?
We have serious concern about how actually we teach, experimental physics in our undergraduate curriculum. That itself requires a panel discussion so that we can put our suggestions.
You call me for that one.
Yes, sure. Yes, and we should put out our suggestions and send it to the NEP committee who are writing the syllabi. I don't know,
curriculum and so on. Yeah.
Yes.
Sritana, if I can just add one line to what you were saying, and it's that it also needs to be experiments where, I mean, just not doing the Newton's ring or whatever, 9.78, again, make people either build something or, give them black boxes and try to figure out, I mean, not just, the answer and you perform the experiment and get it. That has a role to play, but the kind of skills that you actually need in research would be more about, figuring out, for example, when things go wrong, which go wrong many times. And so such things would be more useful to put in a syllabus.
Yes. Actually, we don't have design of experiments in our syllabus. I mean, I think the time constraint is a big issue. That's definitely a problem. But there must be some aspects to it that you can extend experiments. I mean, you do this, but then you extend a little bit of this to have this aspect of how you actually design something, not just repeating the same thing. As Rajdeep was saying, giving instructions, do this, do that, that should go away from from physics teaching. So I think Ognibho Datta, one of our students, he had a question and Rajdeep probably answered that. So Ognibho was trying to say about, this is more of a sociology kind of question, that what role do collaborations play? I guess we all know the answers. I mean, today I don't think we can solve can we solve any important question, any important problem in physics without sitting by ourselves? I don't know. Your take, anybody wants to have a take? Rajdeep already answered, I think, but others?
No, I think we all agree, and this is something, I mean, we have been doing for quite some time. I mean, even when we were students, we were told that collaborations are the way to go. So I think this part is where we all agree, and it's kind of cemented. There are many other problems which we are still dealing with, but collaboration is not one of them. This is my feeling,
So, Tithoda, so I was just wondering that there is some notion, I feel, that in the Calcutta area, it's probably a very, very old school notion that, you have to do everything from scratch, all by yourself. And when you are collaborating with others, that actually is an exhibition of your inability to solve a problem. I think those are kind of rubbish. I mean, I don't feel that they should be encouraged at all, those kind of thoughts. Would you agree with that?
Yeah, no, I exactly don't know what the concerns are. I mean, it's just that, as you were saying, I have never seen a colleague or a student or a faculty applicant who hasn't worked under collaboration. Yeah, I agree that the nature of collaboration varies. Maybe the number of people they collaborate with maybe varies. The kind of people they collaborate with changes. But collaboration is a kind of must, and there is, yeah, I mean, that's all I wanted to say.
And again, it's like a technique. I mean, we don't collaborate for the sake of collaboration. We want to collaborate because we want to solve an important problem.
Yes.
And I don't have all the expertise. So I have to talk to people.
Yes.
I guess that's very, very much probably everybody will strongly agree.
Yeah, one thing, for example, when suppose I'm as a theorist, if I don't talk to experimentalists, how do I know what data to look at?
Yes.
How do I know what is interesting? What is, and by interesting means people don't understand. If people understand, that's no longer interesting, right? So if as a theorist, you are not talking to experimentalists at all, I don't know how without that kind of a collaboration and crosstalk you would do any kind of research even. Yeah.
Yes, I would exactly think so. Yeah. So I'm sure, and Urvashi, you should
yeah, of
be.
course.
Sure.
Yeah. So I mean, yeah.
So maybe then in the last couple of minutes, we may touch upon this issue of representation. So talking about representation, so last night I was talking with Professor Shrirup Raichaudhuri, and I was saying, I couldn't get a moderator, and then students actually asked me, and so I'm going to do the moderation, and then he said, oh, you will do fine. Also, there will be this gender balance. So we now have 2 women in the panel and 2 men. So we have been encountering this issue of representation. So I will not put anything very specific, but maybe it would be interesting to hear from the panelists on what they think this representation issue is and how important it is, and what should we do in our field to sort of address the concerns that have been there. So maybe I'll go with Tit first.
Yes, I mean, of course, this is a serious problem. It affects all aspects of society. Again, if I compare with what the situation was earlier compared and today, I mean, at least in the community, there is an acknowledgement of the problem. I'm not saying this is something to be proud of. I mean, we should have made much more progress, but at least there is an acknowledgement. And in many situations, there is a kind of conscious effort to address these issues. And I mean, at least in my institute, be it admission tests, be it like faculty applications, I mean, various aspects, I mean, this issue is discussed and people try to address. I'm not saying we have been successful all the time, and probably because we often don't reach the root of the problem. I mean, we try to do something heuristically in an ad hoc way. But yes, there is an effort, there is an awareness, and I think we are much better than what we were before. We have a long way to go, but I think at least, again, I'm talking about the institute I work in and nearby places where I am aware of. I think the slope is positive towards this direction. We have a long way to go, but
yeah. So I guess when talking about like gender representation or representation of underprivileged communities.
Yes. Yeah. That also. Yeah. So yeah. Sorry. Yeah. I missed that part. Yeah. So I agree. See, I mean, as you know, this physics research, there is this problem. People coming from underprivileged or less affluent backgrounds have this difficulty that to get a permanent job or some security, you have to wait for a long time. I mean, to do a PhD, 5 years of research experience, and only then you come to that. And many people can't afford to wait that long. And maybe we are losing a lot of students because of that, a lot of bright students because of that. This I agree, Sritana, I haven't seen a very, like, I haven't seen a lot of discussions happening regarding this issue and trying to address this issue. So yeah, again, this is something I have also personally felt that this is a problem. And this is something, again, I haven't seen being discussed. I mean, I have some notions of how to solve them, but yeah, that's a different story altogether. So yes, we should start discussing about these things.
Absolutely. So Professor Sinha, Urvashi, do you want to share some of your views? I guess we together spoke a lot about it. Yeah.
Yeah, we have been partners in crime. But then, having said that, I mean, yeah. So far as the gender bias issue is concerned, I mean, you know, there is one thing. I mean, I agree with Tirthankar that there is, you know, a positive slope so far as that is concerned. And of course, I belong to an institute where I see that, you know, there is a very good ratio even in the faculty level. So we do have a good percentage of, you know, women in the faculty as well. But then one thing that I always find difficult to accept in some sense is that, you know, this feeling of complacency that somehow some of us have, that, you know, since something is being done, then you should be okay. You know, what is, I mean, in fact, I was on my way to this Hyderabad conference, Sritana, where we also, of course, met. And so there, you know, there was this person sitting next to me in the plane, and we just struck up a conversation as to, you know, we're going to, so, you know, going to a conference. So what is the conference? It's on gender, you know, in physics and so on. Oh, is there an issue? I didn't really know that there is an issue. And so then, of course, I had to spend 10 minutes very animatedly explaining to him what is the issue. But then having said that, while maybe there's more awareness that there is an issue, there is also this thing that, you know, because there is awareness, I think, okay, fine. So now there is awareness, something will happen, hold your horses. Don't worry about anything bigger than just people acknowledging that there is something, you know. I mean, so, I mean, you know, if there is going to be a leadership role that is being given for something, it will still be given to the 50+ male, even if that person is not from the field. For instance, in our field, the field is 10 years old. So I'm probably one of the oldest people in this field, in experimental domain. But then having said that, you still need to find someone who's from a different field, but has moved to this field now because it's lucrative, let's put it that way. And then now that person has to be given the leadership role, having worked in it for 4 years. So this is also not something that should be accepted, you know. So there is things need to change at different levels. It's not just about acknowledging and making opportunities available, which is of course very important, but also about ensuring that the representation is there at every level. And you know, we should have more directors of institutes who are perhaps also sharing the same gender as you and me. And so on and so forth. So it shouldn't just be about, you know, okay, are there enough people from the different, you know, from different genders working at you know, at the student level or so on, but because we do have people dropping out. So this leaky pipeline thing that we keep talking about is something which also needs to be addressed. And that is where also this thing comes in, that, you know, so long as we have more undergraduates in physics, I think, okay, something is met, people are aware. So this people are aware and you should be okay with that is also something many of us may not be particularly, you know, agreeable to. So I think there we have a long way to go in terms of giving recognition as well as responsibility without a bias. Mm-hmm. And there I'm absolutely sure even the underrepresented communities who are not necessarily only from the gender perspective, I'm sure there also we have pretty much a bias. Although now there is a new thrust towards, you know, trying to encourage more hires in that and so on. But it also seems like more of an exercise than an actual, you know, something that one wants to do. It's more like they have said, so let's put out this advertisement and then see what happens, and then we'll go back to behaving as we were doing. So it shouldn't be an exercise. It should be something which comes from within. Yeah,
absolutely. Completely agree with you, Urvashi. And as I think I put it out in this way, that whenever we think about representation, the first thing that people say is that we want to give equal opportunity. But yes, definitely there's a question of equal opportunity. We have public institutions, we are running our institutions in public money. That part is fine. But then from the more intellectual and, you know, field perspective, I think I agree with what Professor Meguri 20 years back told, that it's about extracting talent. I mean, nature doesn't give talent to males coming from, certain males with certain titles, Banerjee, Chatterjees. This is not where all the talent is being dumped. So it's a talent is random. It's the central limit theorem. So we have to be very inclusive, because for the sake of the field, because we want to have the best minds coming to our field. So Rajdeep, maybe some of your thoughts on this?
Representation, as both you and Urvashi has been more involved, at least from the gender perspective, and you probably know the issues better than me. One thing I would say is that, gender, not that it has been solved, as Tirthankar was saying, there's at least some acknowledgement, but for other representative minorities, the acknowledgement is also probably not there.
Yeah.
That's just one point. So of course, people in principle always agree that diversity is a good thing, we should have all of this, and the question, of course, as you guys you've been pointing out, that what are you doing practically to change that? So I can tell you one experience. My experience with this was that 2 years back, TIFR started a program called Vigyan Vidushi, where they basically started for first year MSc women students. They were doing summer school, and that summer school did not just focus on teaching physics. It did that, but there was a lot of mentorship sessions, and prominent women physicists were giving talks, and they were also part of the mentorship sessions and so on. And this was in some ways trying to, I'm not sure this will solve what this is a way even to solve, but this is an effort to solve the leaky pipeline issue to some extent, where, we found that many of these students were being pressurized to go into marriage. Various other, that's just one aspect, there are various other things, etc. People are not very, their parents are very unhappy about them going away from their hometown, and all sorts of things, which of course have this. Now that's not going to solve the full issue, and full issue requires a wider. But just to, I asked before I came here to the organizers, so they have been taking this idea that they should at least track, is there anything coming out of this effort? And so this time, apparently, we asked the last year's Vigyan Vidushi participants whether they have applied to, they have been accepted in physics, whether they don't want to do physics 1 year after they attended the program. And 79% of, 47 people attended the first program, and 38 of them responded. So the rest we don't know. You can take your guess what happened to the rest of them. But out of those who responded, it turns out that 79% were in some stage of applying for a physics PhD program. And 21% said that they are leaving physics or they don't want to go into physics. This 79% includes people who have been accepted, who were in the process. Some said, they tried, but they were rejected. So they're thinking to again apply next year. So all of that category introduced. Now, this is a complex problem, and it's not a sociologist to give you a recipe to, of course, we all agree that, as you said, that, there's no monopoly on talent. And not only that, the sociology of the field, when things are diverse, also affects what kind of physics gets done at some level, in a very nebulous way, maybe initially, but, over a long time scale, it does affect. We have a huge population bonus, okay? Young population, and not getting representation from a large section of them is doing a lot of harm. I don't have an immediate solution. It's unlikely to be an immediate solution. I mean, and probably you and Urvashi would be better at talking about solutions than me. But I think the other thing that is happening is that sometimes even people who are graduating, coming in, doing PhD, okay, even after PhD, they are leaving. So, you know, they have already gone, and at that point, part of what Tirthankar says probably plays a role, part of not having opportunities plays a role, and so on and so forth. I don't know how to solve the bigger problem, but maybe this problem where people who have already done PhDs and our profession kind of takes a very long time, 5 years of PhD, 4 or 5 years of postdoc. That's like, you know, standard 10 years you are asking someone. And then at that point you are saying, there's no guarantee that you will get a job, but you know, if people do well, they get a job, etc., etc. Maybe we can or should try to alleviate this part. Maybe younger postdocs who are being hired, maybe, you know, so that we can get more people at the faculty level, etc. Of course, attitudes have to change, and you know, professions often work on their own professional logic. You know, there's a logic of merit. There is in bankers. There's a logic of getting shareholders' money. That's the biggest thing. And ultimately, of course, it's all a political act. We are working with public money. We are living in a society, and so on. So, yeah, I mean, attitudes I can see are changing, but as Urvashi has said, it's gone only up to the acknowledgement. I don't think it has gone beyond that point, or what time scale will it take to go beyond that point? I think you and Urvashi have a better idea than me. What I would say.
Okay.
But I do hope the future of the physics workforce is much more diverse than it is today.
Yes.
I do hope that.
Absolutely. Absolutely. We all hope that, and we hope that we never have to talk about diversity in any of the panels 20-25 years down the line. I mean, yeah, we should, but I guess it will become more and more even. The distribution will become more and more even. So I think we all of us spoke for a long time. And so maybe the final take, so just 1 or 2 sentences. Take the liberty to very bright, but I would just maybe then this time I'll go reverse order. So first Rajdeep, then Urvashi, and then Tirthankar. Just tell us a few lines for the youngsters who are present in the audience today, and I guess we will wrap up because it's 2 hours. Yeah. So Rajdeep, just
I'll tell one thing. Physics is really fun. I mean, you know, whatever you do, just tell you a little bit of the fun. I mean, you know, we wake up, most of those of us who do it for a living, wake up most of the days, and this is something that you should be careful about, not figuring out what we set out to figure out. We fail very, very often, okay? And, but we love it. And when we succeed, that high is what sustains you till you fail, keep on failing for the next, you know, time you succeed, okay? So come and do whichever part of physics you like. Don't be afraid to fail. I mean, you know, that's just part of the profession. It's baked into the profession. Because when you succeed, it's really, really worth all the failures, all of those days. And that's what keeps us sustaining, figuring out these puzzles of nature. So I welcome all of you to join the community.
Thank you. Urvashi?
Yeah, I don't think one can say it better than what Rajdeep just said. So, I mean, you know, troubleshooting and enjoying the act of actually figuring out the smaller problems towards the bigger problem that one is trying to solve is what makes everyday life a lot of fun. And even in the experimental domain, you know, that is what it is. So it is, I mean, you know, you don't really, I mean, as I keep saying that, you know, 90% of the time is troubleshooting, and it's perhaps only 10% where you have those eureka moments. and you know that, okay, this is now starting to look like what you may have envisaged, or something completely different a lot of the time as well. And so then you have to figure out why. And so a lot of the fun is actually in the process of the smaller questions and solving them towards the bigger challenge that you set out to do. And so I think curiosity is what will actually bring us, take us a long way as physicists. So students, inherently they are curious, and so that is something they have to retain. I also would say retain that wide-eyed wonderment. Our education system sometimes takes that away from us. We get very bogged down. So I think retain those, those naive questions. No question is naive, really. Those are the hardest to answer. So if you retain that wide-eyed wonderment and curiosity, and have fun in solving the little things every day, and then, not worrying about it at night, and then again coming back and solving, I think you should become a physicist for sure. Yeah.
Good. Great. Siddha?
Yeah, glad that you asked me last. I have nothing really more to add. I will just address the students and tell that, again, I mean, since I'm probably addressing many male students in Bengal, the distinction between theory and experiments are getting blurred day by day. And very soon, probably the next generation of physicists will be, the best ones will be those who can do both of them like equally together, along with, so it depends on the field, of course, so along with numerical analysis and other things. So yeah, I mean, try to take like every aspect of physics seriously, and if you do that, it's really fun. I mean, so there I completely agree with the way Rajdeep put it. Yeah.
Okay.
So that's all. Yeah.
Hey, so thank you. Thanks to all the panelists, and thanks to the audience, enthusiastic audience, and particularly I see a lot of physicists also in the audience. Our colleagues are there. Thank you so much for joining us in the panel. So maybe this is the last line, and it's already 8 o'clock. So we are up for dinner. And I feel that today's panel concluded that physics is really fun, and there are a lot of interesting problems that have to be solved in physics. And I guess the future will really depend on how much enthusiasm we can extract from the younger generations who are in the audience and who will be doing this panel. And it will be even more exciting when we are able to extract and pour the curiosity, the enthusiasm, and the commitment of our younger generations. Maybe that's a good conclusion of a panel, rather than really thinking that what are the important problems in physics. There are a lot of important problems in physics, and we must be enthusiastic about what interests us.
So Sritana, as probably Lincoln or someone, as these quotes keep going, the best way to know the future is to build it yourself. There's a quote like that. So for all the students, it's in your hands what the future will look like.
Yes, that's right. Okay. So thank you again. Thank you very much. And maybe we stop here. So, and thanks to the organizers for giving us a chance to do this fantastic Adda all together. Thank you. Thank you, Rajdeep. Thank you, Tirthankar. Thank you, Urboshidi. Okay.
Thank you very much. And it was
Thank you.
a wonderful discussion.
Thank you.
Fantastic.
Thank you very much.
Fantastic. Fantastic. So maybe we should now stop the live streaming. Yeah.
Bye then. Oh, you're going to stop the live stream. Okay, bye.
Yeah, I'll just stop the live stream.